All right, hello and welcome back to the DOTS lectures. Last time what we were talking about is the is how we can use some abstract nonsense to discover and construct the discrete op vibration classifier for double operatic algebras, which is rather fun. So just as a brief review of that, I'm going to scroll back up to where we were doing that right here. We say, what is omega? Omega is the discrete off vibration classifier, which is a super technobabble name, but it means this is where the representable functors land. And so we've seen we had these pictures for the various different kinds of things that can occur in these sort of pasting diagrams or string diagrams for double operatic algebras. So we had the operations here, which take the place of our interactions. We had the systems, which are going to fill in these little bubbles. The wires are the interfaces, and then you can fill bubbles by trees that only have bubble leaves, or that it's not true that they only have bubble leaves, that they only have these things in the back and no wires coming out of the back. And similarly, you can fill triangles by anything that does have wires coming out of the back and does not have any leaves of these bubble sort in them. And we used the Masiti construction to understand what the discrete off vibration classifier was in pre-sheaves on the underlying data here, which are all these are all these various shapes. Um, and what we found is that again, it's very much like the other time we did this. You have a system is in fact a map into an interface, like here, projecting out some variables. An interface is just a set in this case. And then this time a composition law, a coupling law is a span, but not a single-legged span, it's a multi-span. So it has many legs in the back and a single leg up front. And then we still compose by taking this limit. Okay. So now with that idea, so because of that, so for this reason by the abstract nonsense I described before, by the theorem that I approved with Matteo Capucci, omega, as described above, i.e., span, in this sense, acting on the slices of set, right? Which we've called before the Jan Willems behavioral style theory with no notion of time baked in. Um, classifies discrete op vibrations. And so, as we said before, if we have a Colac morphism into any operatic algebra, this thing here is a double operatic algebra. So in other words, it's a double operatic and an algebra, right? We can form the slice. Let me call this A down arrow A. Right? And in this slice, this map here, this projection, is in fact a strict discrete op vibration. Right? So therefore, it classifies, yes, it's important to note, it classifies strict discrete op vibrations. So we get a map. The projection here is classified by some map, which I'm going to write as a dash, which goes from A to omega, and this is only lax. But we still have this pullback square. Maybe try to be consistent with my notation here. Okay, so let's understand what this thing does. So is the way the classification goes is it sends an object in here. So it sends an object in here. So let me say that again, well, we should look at what this does on every single feature. So let's blow this up a little bit into here. I'm going to have a systems and then a interfaces. And then, we'll just consider one of these. And here is a interfaces again, something like this, right? Of course, this is for, maybe I'll write dot, 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 because we have a lot of these, right? One for each n. It's the difference between this and the other theory. And here we have set arrow, and here we have set, and here we have set with the multi-span, and here we have set again. And we can try and understand what are all of these maps, right? So A in here, so I guess before we do that, we should really understand what does it even mean to be a Collatz morphism like this? This is all abstract nonsense. We get the thing out, but like now we do the fun part of category theory where you package everything up, you prove a nice little cute result, and then you unpackage it all again. So it's all wrapping and unwrapping presents we make for ourselves. That's category theory. So what the hell is a Collatz morphism of double operator algebras? So we should think about what the terminal double operator algebra is. So before we can do this, we have to think about what's this? So maybe I'm gonna see if I can fit it all on the right-hand side of the page, right? So first of all, star is the terminal double operator algebra. And so it star of everything is just, well, what you would write as star or the set containing star, a terminal set, terminal category, I guess, because these are all categories. So what does that really mean? Well, it's actually different than what we got last time when we computed this. Because if you remember last time we did something similar with loose right modules, right? And we took the terminal loose right module. In that case, we only had one kind of interaction, which was a unary interaction. But now what we see is that the algebra of interfaces here, yes, there's only one interface. So there's one interface, one system, but then also one interaction and of any arity. And that's different. Oh, yeah. Sorry, I hope that's not on the recording. That's fine. Yeah, let's not make that out of it. Ah, thank you. I hope that's not on the recording. Okay. Right, one interaction of any arity. And that's different than what we had last time. So now when we take a map star into A, right? We go, let me go ahead and just put that down here, right? We have star, 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 right? So what is a map? Well, it's a bunch of these things. Again, these are all equalities. There's only one map you could possibly put there. And so I'll call this thing A. I'll call this thing the interface of A. Why not? And then we also have, for every n, we have CAN. And this is also the same interface of A. And that's actually a lot more than what we had last time. So, and then we have all the colac structure. So this consists of one, a system A, two, let me just say with interface A, IA, two, for any n, a interaction IA dot 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 IA, and this is n times. So maybe I should be more clear here and say for every n, like we need all of them. Okay. And then we have the colac structure, right? And so in this case, what does the colac structure mean? It means that every time you would write out on a composite that you would expect to be equals if you were doing a homomorphism, you put in a map. So in other words, we're going to get a map from, let's say, and this is what I called CAN. So we can take CAN and we can apply it to A n times. And we would expect that this would be equal to the result, right, of I think I have to go maybe I want to go the other way. Well, so this is an action. This is the image, right? So this is, as you can see, this is something like this is equal to this diagram computed in A, right? But what if we computed that diagram in star? Well, it's just star again. Star only has one thing of every kind. So the image of that is in fact A again. And so what a colac morphism also has is these gamma n's like this. For any n, we have a map from A to this composite of A with itself n times via this law, which was part of the data we had to add. And this has to satisfy some laws. And those laws are that the laws are that, if you will, if you do this multiple times, they compose in the flattened version, right? So the law, of which there is really only one, is that if I take A and I split it up into CAN A dot 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 A, and then each of those inner A's, so this is gamma n, each of those inner A's, so I have CA comma n, sorry, I do have more data. Excuse me. I wouldn't have been able to finish this diagram if I didn't have the more data. This was for diagrams of this shape, but there's also diagrams of the other shape, which is that we have the composites we're allowed to have here are, let me just, these kinds of composites. Right? So again, we interpret this both in star and in A, and then move them both to A. Right? Let me put a cell in between. So what does that mean? Well, here, this outer one is CA, comma, sum of NI, where each of the back ones here has size NI. And, there are this many, we're summing over this many of them, of A's, you know. And then that's what happens if I take this diagram, evaluate it in star, and then move to A. But if I instead evaluate each piece of this diagram, I'm sorry, shouldn't be a circle, it should be a triangle right here. Hopefully I can get rid of the circle. Oh.
Should there be A's?
Oh yeah, it's not actually necessary for this to be A's. It's in fact just the thing itself. Thank you very much. It's the operation itself. Right? And then the other thing I could do, right, is I could take the innards and compute them all. Right? So in this case, I'll do, we'll take this family. I've been writing this differently the whole time, so I'm going to remember that I was doing that. We write this as A dot 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 A dot CAN. And then I'll do that again. CA here, right? We have each of these NI and one dot 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 CANK. And then we dot it with CAK. Right? If we're summing up over K of them.
And that dot is like technically different.
Yes, this is I think I've been using the same notation for both of them. But yeah, that's right. This is the action of interactions on systems, and this is the composition of interactions. And there's an associative law between them. Have I been using the same symbol for that?
In the loose right modules that we were.
Tensor? No.
No, I think we're using the dot and the dot for both the action
and the, yeah, I think we were, yeah. Okay. Right. So in this case, now we need the composite of them. So in each one of those, each one of these inner ones, I can split up into, let's just say N1 of A's, dot, 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 C. Oh, yeah, I do. Thank you. Okay. So this is A. I'll just write vec A. It's always there's only one length we could possibly do. And then we take each of those inner ones, right? And we expand them out somehow. Right? Huh?
K.
Yes, that's a K. And this one should be a K too, I guess. And then now we can associate this as a whole bunch of A's. There's more A's in this last one than all the previous ones, right? Or, I mean, it's exactly the same number of A's, but they've been rearranged out to this side, acted upon by this. Okay. Way down in the corner over there. Can I get maybe a little more? Okay. Here we go. That's all right. A little bit in the middle up here. Right? Or I could take A and I could expand it all the way out into the sum. There's also associated, like, there's more laws than this, but I'll just draw this one. There's also the laws that this is a law that corresponds to 3, and there's also a law that corresponds to 4. 4 should probably have been written before 3, sort of logically prior. It gets used in this one, but here I can expand it all the way out into a vec A dot C A comma sum of the ni, right? And then I can expand out like this. So if I call this delta, right, then this is also a delta, this is also a delta, and this is an alpha unassociative. And so that has to commute. It's one of the laws. And then the other law is the associativity law just for the deltas, which say if you have a two-layer composition, you do both. You could express these also in a more general abstract way by looking at the diagrams you actually use to compose, and any time you have a twice nesting, you give a anytime you have a diagram which is singly nested, you give a two cell like this, a transformation, a map. And then every time you give a twice nested diagram, you give an equation between the thing you get if you did it if you collapsed it and then took the map associated to that, or if you didn't. So I don't know if I should write that. Maybe I'll write it like kind of as a general sort of thing. No matter what shape, I'll give you a here's a more general diagram. Hmm. Here's a diagram for composing three systems, right? Well, let me, yeah, here's a diagram for composing three systems. And I'll say that I can do this in two steps by adding a middle layer, which I'll bubble up in green here. Um, maybe yeah, this one's not a tree. I'll make this more tree-like. I'm a little, I don't know. Yeah, we'll make this more tree-like. It'll be fine. And then this will be boom, boom. Okay, there we go. So there's our middle layer. So this is what I mean by a twice nested diagram, right? So there's two kinds of things we can do. So each one of the inner ones gets associated with a cell, right? And that cell is what we could call A of each one here. So A of, say, the top one is like this. Um, and that goes, that this, but then bubbled up is going to be a transformation from A of this thing, where we compute that in the domain. This is the domain only has one thing, but it's sort of somehow more illustrative if we define what a general Colac transformation is rather than this specific case. In fact, we will have need for that later. And it's a map that goes from there to A of the outer. And so if I write down what this is, right, you see that it's this thing we wrote down. That was the wrong way around. That would be lax. This is colax. It goes from A of the outer to the inner, to the evaluation of the inner. Sorry. Um, let's be very clear about this. There's only one thing in here, so I'll actually fill them. It's better to understand it like this. Right? And this happens this gets interpreted in A, whereas this is being interpreted in star, essentially. Does this make sense, right? You take a nesting, and then you give yourself a two cell, or in this case, a transformation between the A evaluated at the inner, which I could also write in this way, right? It's like We evaluate it A of star, like that. And that map which is what I was calling A above, into this diagram, but evaluated now in the algebra that we're going into. So this being evaluated here, if I write out all the pieces, maybe it's even clearer, so I will do that. Excuse me. So this I'll just call it S1, S2, and C. Right? So here I take filling in here. This is A of S1, S2 dot C. As in, we evaluate the inner picture in the domain, and then we apply A to it. In here, we take each of the inner ones and we apply A to it. So this is AS1, AS2, and AC. And so this is AS1, comma AS2 dot AC, right? And as you can see above, if I make the name CAN for this C is the unique one of degree n. So if I call that CN, then ACN is what I've written up there as CAN. But I have this map. Then for any two layers, right? What you do is you look at the multiple different ways that they can be combined, and you say that there's an equation between them. So I will write this out here. We're going to start with the full inner to the full outer. So we're going to take it and we're going to completely flatten it. So we ignore the greens. And that goes from, what we'll say is this big one into this one. I'm leaving the notation up in that top corner so you can compare this. We're doing the bottom path right now. And the top path is we take the big one and we split it into the green ones first. Like that. And then we split each of those. Well, it looks the same, but technically there's an isomorphism between them, so I'll just leave it here. We split each of these, right, into its components. This is a triangle. And these two are equal, or we'll say they're really everything is wrapped in A. So they're really that these there is a difference between flattening and not flattening, which has to do with these structural isomorphisms that I'm not covering here, but they're the exact same as they work in the double category case. So this is your alpha. And as you can see, this is your sort of gamma, or like these are your there in this case it's a little mixed because this one was a gamma and this one's also a gamma. And this one's a mix of gammas and deltas, in fact, I believe. Or maybe it's just no, this one's just yeah, this one's just it's a mix of gammas and deltas, if you will, although the delta for the triangle one here is an identity. Okay. Does this make sense, or did I make it worse by going into this?
Makes sense. I mean, this is unraveling the notion corresponding to Kodak's morphism of algebras for the two monad. Okay, yeah.
Yep. The two monad, right, sends you from a diagram to its interpretation. And a Kodak's algebra, right? If I make it B. A Colak's algebra goes up like this. This is A. This is beta, the interpretation, alpha. I guess I don't like those names. I've already been sort of using those. These are the interpretations. This is TA. So what this says, if I call this gamma or delta, I've been using too many names here. But what it is, as you can see, is a map that says you take a formal composite and you're going to have two things you can do. You can interpret it in B, and then you can apply A, or you can apply A to the pieces and then interpret in A. And what you get, right, is a map this way called gamma. And that's what we've been doing. And it has to satisfy some sort of natural associativity and unit laws. The unit laws, which I didn't describe up here, say that if you're boxing up the same diagram, it's an identity. Oh. That's in a situation like this, where you just put the same diagram again in its own box. No, same shape again in its own box. Okay, cool. Having a little snack. All right. So that's all the data we have for one of these Colak's morphisms. And let me give you an example. So e.g., consider the double operad algebra, which is graph, or what we could call cospan graph, or maybe I'll call it like graph sliced over, sliced under the inclusion of discretes being acted on by cospans, in this case, multi-cospans of finite sets. So this is something we've seen before, i.e., we have a graph here. We have a map from boundary of G, which is a discrete graph on a finite set. And the way we compose is the exact opposite of the other picture, right? Is now by having something like this, and we take this colimit. And then this becomes the new boundary. And that is the same thing as what we did when we covered the right module of graphs all those years ago in 2025. So my claim, okay, so, right. But let me tell you what I want the morphisms to be, because really what I should have said here is, in fact, cap restricted to free categories. So again, the objects are still graphs now. And the morphisms here are still going to be maps from discrete ones, so it all works here. This is a cospan here of finite sets, which, as we discussed, is a kind of bubble diagram, right? So as we discussed before, you can draw such cospans as diagrams like this, where they come together, they meet, they go out, maybe they just meet and go out, maybe they don't. You hide them, something like that. And this expresses a way of gluing some graph here with two marked nodes. So, some graph here, two marked nodes and maybe some other things going on, whatever. We don't know. And then some other graph here with three marked nodes and maybe some other nodes, whatever. And the way you glue it together is you look at which node corresponds to which label, and you set them equal. So this is going to be giving you just trying to look at what I wrote down here. Something like that. And then we put this in a box, and it has 3 wires, just like the outer box there. And they point at the nodes that you would get if you followed everything in. Okay. Now, the reason I switched a little late to categories restricted to free categories is I really do want these graphs and I want them to compose by push out of graph and all that stuff. But I want the morphisms to be a little more interesting. It's actually very important for this that I use this. So a type morphism, aka a homomorphism of systems, right, is a map from G to H. Right? That commutes with the boundary, right? But this is a morphism of free categories. So in terms of the graph, it would be a graph homomorphism to the graph of paths in H. I could write it like that as well. And that's going to be very important for us. The difference between those two is going to make all the difference. And we'll see in a second, because I'm going to describe a Colax point of this operad algebra, double operad algebra, and you'll see immediately that we could not describe the colaxators if we didn't have this freedom of extra freedom in the morphisms. Okay. So what is the point? We've actually seen this before, this entire setup before in the, I believe we went through this before. Maybe not in the dots lectures, maybe in a different lecture. It's the pair of pants.
I think it might be in the Oxford, one of the Oxford seminar videos.
I see. Okay, so maybe a different different thing on the website, but let me call this thing A because I don't want to write it out all the time. So I'm going to give you an example of a Colax point, and I'm going to call it delta 1. So remember that I had to give you a system. That system I'm going to give you is delta 1. I also have to give you its interface. Its interface is going to be boundary delta 1. So what is delta 1? It's going to be this graph, 0 to 1. I'll call this thing 0, 1 bar for lack of a better name. Boundary of delta 1 is going to be just the set 0, comma 1. And we're going to take the obvious inclusion. Okay? And for any n, I have to give you a multi-cospan. So this is what you would call A, and this was IA. And then I have to give you what I called CAN. And CAN is a cospan from n copies of delta 1, like this, something, and then a final one over here. Now, remember, this is a cospan of finite sets. So I can draw it. I can show you what it is by drawing it. So I'm going to do that, and then we'll tease it out. So we have n inner boxes. Well, I have to draw a few of them. I can't just draw none of them. We have n inner boxes. And each one of them is a 2-element set. So we have 2 wires on each one. The outer one is also a 2-element set. So here's what I'm going to do. I'm going to take this left endpoint and I'm going to pass it out. I'm going to take this right endpoint and I'm going to pass it out. And then each one of these, I'm going to connect to the next. And that is my generalized pair of pants with a lot of legs. Um, the binary pair of pants, if I did this binary, we get this picture. And this, if you look sideways, is the pair of pants. So that's what Mason meant by it's a pair of pants. It's a pair of pants for an octopus of n legs. I guess an n bus. I don't know. An airy octopus. Anyway, moving on. What does this actually look like as a cospan? Well, how many inner bubbles are there? Right? How many of these things are there? Because that's going up here. And if you look at it, there's one in between every one of these n things, right? Which would be n minus one of them, and then two more. So it's n plus one. So this is a set containing n plus one things. We could write 0 to n. And each one of these, if I was very nice and decided to write them out like this with duplicated names, 0, 1, 1, 2 instead of 0, 1 again, right? 2, comma 3, and so on until n n minus 1, comma n. That tells you what all these maps going up are. I've now renamed them by their image under these maps on the left. So I have a bunch of two element sets. I originally called them 0, 1, but if I rename them like this, it tells you exactly how to put them in to that middle one. And similarly, we'll call this 0n. Okay. And that shows you all these inclusions. So that is in what way? So now I have to tell you the collax structure here. So let me just do the one that corresponds first. Let me just do the one that corresponds to this diagram. Right? In other words, remember that I need A maps to A dot C2. Right? So why do that? Well, we can draw it out quite fully. I mean, we'll see how it generalizes here. But here I have delta 1. I have a copy of delta 1. I have another copy of delta 1, and I have their boundaries. And they include. So let me, instead of writing them out with names, let me write them out with pictures. Here's 0, 1. Here's another copy of 0, 1. Here's 0 and 1, the boundary. And here's another copy of 0 and 1, the boundary. Right? So A, IA. Here's 0, 1, 2. And then out here we have 0, 1 again. This is the map of 0, which I could call just 0, 1, as in 0 maps to 0, 1 maps to 1. And this is the map 1, comma 2, as in 0 maps to 1 and 1 maps to 2. Another way, simplex people might prefer to name these things by the one they don't hit. But I'll just keep going here. Well, it becomes very nice if we say that here. This one also you might call 2 hat. This one you might call 0 hat, and this one you might call 1 hat, as in I missed those. Okay, anyway. Now I take the push out or the colimit up here. What is the colimit, right, of this thing? Well, what I do is I take this, I put in both graphs, right? 0 to 1, 0 to 1. And then I'm going to set some things equal, right? So I'm going to set 0 equal to 0 ultimately, right? I trace it through. This 0 comes from here, which goes to here, which doesn't connect anything down there, so it just goes all the way out to here. So that remains the same. Similarly, this 1, well, it goes out to 1, goes up to 2. 2 doesn't connect anything up there, goes out to 2 or 1. So this remains the same, although it should be renamed as 2. It's not strictly important that we do that, but I'll just do that anyway. Now we get the interesting bit, right? This 1 goes out to this 1, which goes out to this 1, which connects up to this 0, which connects up to this 0. So they have to be set equal. So in fact, I don't have 2 things in there. I only have 1, which I will call 1 because that's what it's called up here. And then you see that the ultimate boundary here is, if you will, 0, 2. Okay. So great. We've computed that. I need a lot more space, I suppose, for how big I'm drawing. And then we need, just to remind you what we're trying to do, I'll bring this down. We need a map from A down into that. So this thing is our new system. That is this. And we need a map from A to that, which is A is again 0, 1 over 0, 1. This has to be the identity. It's one of the actual rules that I didn't write down before, but because there's no double way to bundle up a wire, the wires don't have collaxators. They have to be fixed. The wires correspond to the in the pictorial point of view of operatic algebra composition correspond to the interfaces in the system's point of view. Everything here. So maybe I'll draw that in green so that we can draw the whole collaxator stuff in green, just to be, because this diagram's getting complicated. So, and then here is going to be our gamma. And the question is, what can gamma be? There's only one answer, right? And the reason there's only one answer is because we need the square formed by the greens vertically to commute. So in other words, 0 here has to go to 0 here, which has to go, well, wherever 0 went here, which is 0 here, and 0 goes up to 0. So we know that 0 goes to 0. 1, on the other hand, is marked here by 1. So it has to go wherever 1 went, which was 2. So 1 has to go to 2. So 0, 1 has to go to some map between 1 and 2. And if we didn't allow ourselves to take paths before, we wouldn't have a place for it to go. But because we were taking this push out in categories, or alternatively, because we defined maps to be Kleisli maps for the path monad on the free category monad on graphs, we do have a map here, 0, 2, and we define gamma of 0, 1 equals 0, 2. And hopefully you can see that this situation is just mimicked if we go back up. If we look at the n-ary one, right? Again, if I draw my little graph here, you see I end up with a little arrow in each one of them. So this obviously reduces to a sequence of n arrows because we glue each endpoint to itself, bounded at the ends. And there is a unique path or a unique choice that makes sense, or literally there's a unique choice of how to send one arrow into a path in n arrows that preserves the endpoints. I have to send it to the whole path. And so that's what I take gamma n to be. This one here was gamma 2. Right? Okay. And so I should also, I guess, talk about the Colac structure on these diagrams. Although I think it may actually just be pseudo. Let's try and write it out. I'm going to do two of them nested, and we'll see what happens. So here's one pair of pants, and let me put a pair of pants in each pair of pants. Cool. Now what happens when I erase the middle pair? What do you know? It's just more pairs of pants. So pairs of pants actually compose on the nose. Or, well, technically we did all these namings, so there's like a canonical isomorphism there, but like whatever. It's not collax. We don't need anything special about that. Okay.
Sorry, I'm still amused by the fact that the map on the interface for the codec,
Down here?
yeah, must be an identity.
Yes.
Is that somehow related to the pseudonymous?
It happens from it's part of the unit law for collexitors. Okay. So the fact is that every identity is the interpretation of itself. So, sorry, every interface is the interpretation of itself, as in it is in the image of eta. So it always has an identity for its collaxitor. It's fixed. The interfaces are fixed by the, if I go all the way back to my algebra square, I don't remember where that was. Not that far. Here. Any wire in here is the interpretation of that wire. Any interface in A of the wire is the interpretation of the wire up in here, of itself.
Right.
By eta, right? It is the image of eta. And that's because there's nothing you can put in a wire. There are no formal expressions that you can fill a wire with.
Right. Okay.
And so all wires then are in the image of eta. And one of the rules that I didn't talk about is that if you whisker gamma by eta, you get an identity.
Right. Yeah.
Where eta here is the unit of this junction. It's one of the laws of being a Colac morphism of monads, which I don't know if I should cover, or maybe I did cover. I think I covered lax ones. Let's take a stroll down memory lane here. No. 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 All right. This could take that looks Colax. But did I ever cover the equations? I think I did a two cell. Maybe I should have done the equations. They're not terribly difficult. Would it be helpful?
I think I now understand why.
Yeah. I don't know. Maybe. Would it be helpful? Yeah. Okay. Okay. Yeah, listener, if you're this far and you don't know the equations for a Colac morphism between monads, you can look it up on the NLab. I'll try and bring these back to Earth in some near time frame from here. We're about through with the overwhelming two categorical machinery portion of the dance lectures. And they'll be likely reborn with a much more practical focus over the coming months. But not to get ahead of myself. Right, this is a Colac morphism. This is a Colac point. So all this structure is the structure of saying that I have one Colac point of this algebra for double operats, which is graphs, or a Colac system structure, right? But now this is really nice because actually we've seen the pair of pants before, I believe, or again, not maybe in this lecture series, so I should go for it. But we can see something really nice about what happens when we map out of this specific system. So let's say I have a general graph here, which I'll draw, something like maybe. And then maybe I'll call this A, C, this could be A, B, C. And then I'll make that the boundary. I could have made all the nodes the boundary for all I care. It doesn't really, this is not important. Someone has decided to make this the boundary of this graph. Okay, let's see what a map in from our friend. Why am I drawing in purple entirely? I don't know. From our friend the arrow. Right? So remember, a map of systems always begins with a map on its interfaces. And the map on its interfaces sets the stage for us to compute the map on systems. So for ODEs, right, you needed to choose your parameters, and you did that by choosing the map on interfaces. Here, what is a map on interfaces? Well, it's a function from 0, 1 to this set ABC. And such a function picks out 2 points in there. So maybe I'll say it's AB. Right? And then a map here that lives over it, that makes this commute, like a map of these actual systems, sends 0, 1 to some path. But it must send 0 to A because it needs the square to commute. And it must send 1 to B. So maybe it sends 0, 1 to this path. But there are other choices, right? But note that it might not be able. I should let me go ahead and pretend I planned ahead, right? Well, it might not be able. You might not be able to do this, right? Because if I had instead said that we needed to go to C, then this would have gone over here to C, and then I would need a path to C. And because I planned ahead really well, you can't do it. There's no path from A to C. So as you can see, one of these things here is what you could call a reachability problem. I.e., a map, I'll call it boundary delta 1 to boundary G, is a reachability problem for G. It's just a pair of points, right? But I'm thinking of it as asking, can I reach the second point from the first? And then a homomorphism here okay, is a solution to the reachability problem. Okay. Okay. So one thing we can think about is if I take my functor A, we have A mapping out of delta 1, right, which we're guaranteed to have because it's a collax point, and it goes from A to omega. Well, we can say that on interfaces here, on boundary G, it maps to the set of reachability problems for G. For, let's say boundary G. Right? I.e. pairs of points. And then it sends G to the set of to the set, if you will, to the set of pairs of a problem and a solution. And of course, it maps down, mapping down, right? So this is in set. as you can see. And this is going to be in set arrow, which is what systems are in omega, right? G, and technically G has an included boundary, into the set of problems, right? So we can think of this as being a display map. We've noticed this before, the idea that really this is not a map so much as like a map that does something, so much as a projection of some data. So really you want to think of this instead as a family of sets, namely the family of solutions indexed by the set of problems. Of course, the image of this are the solvable reachability problems. So now, well, now let's think about what does one of these CNs get mapped to, right? So in this case, right, we have boundary delta 1, dot, 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 boundary delta 1. We have here, which I'll call n, because that's what we call the set 0 to n, boundary delta n. I could even get rid of boundary delta 1 and just call these 1. Maybe I should have done that the whole time, but we're leaving it. And here is my generalized pair of pants. And now I want to map this out to things. Well, I map it out to general composites. G1, Gn. This is a new one, J or something, and this is C. And these are the other wiring diagrams. These are cospans of finite sets. And we send this, this thing here, this maps to the set of all such things. I'm sorry, I did that wrong. This maps to the set. Let me rearrange a little bit. Bump, bump. And we'll have this thing here. Move it up here on the left-hand side. This wiring diagram maps to the set of all, vertical maps here. So, if you will, what is that doing? Like, what is that? How do we understand what such a mapping is? Well, if we draw the bottom as some kind of wiring diagram, and I've been writing them all in a row, but maybe it's better not to write them all in a row and to write them as just a nest of bubbles so that I don't have this sort of sense of like, because they don't have to only talk to the neighboring ones, right? I kind of fall into the habit of doing that. But this one might connect into here, and this one might connect into here, and also something from here. And this one might go out, and this one might go out here, and this one might go out or whatever. So what is a map from, say, a two-ary from C2 into this, from this thing with n equals 2, perhaps? Well, it will be two boxes. Actually, sorry, I need the same number of boxes as things. So Cn, so all boxes. But now what I want to do is somehow map the shape of the pair of pants onto this picture. So for example, I could pick this green one and this green one for my ending. And then I have to pass them into the next one. So this one goes into here, right? And then this second box over here, right? This has to go to the next one, but I can double it up, go like that. And you see it's a really weird squished pair of pants. But the point is maybe you can see that I've mapped this shape right? I've sort of mapped it into that, where these both got sent to the same point in here. But nothing said I couldn't do that. Okay. So now what does laxity say? Because that's the other, this is what all the data does. Set all the data. Laxity says that if I have that for any of these, any maps like these, right? And for any family of solutions to problems on the inner graphs, I get a solution to problems on the outer graph. And how do I do it? Well, if you look at like this diagram, right? There's some big mess in here of all of them with a lot of edges. But if I had a solution on the inner graph, it was a solution from this wire and it went over, maybe I should do it in a different color. Solution, it was a path and it went, around and whatever. And then it came back out on that one, right? And similarly, this one started here. This is a pretty simple reachability problem. Well, I guess not if you don't, depends on how you feel about loops. But maybe it went around like that and came back to the same one. And then this one here started here and went around and then it came out on that one. And I think it's pretty obvious how you combine these together to get a reachability all the way from this to this, which is you just do them in sequence. And that is induced by the colaxeter. Because if I take this diagram here, copy, I'm gonna put that down here, paste, right? And we have our G1 dot dot dot, our Gn, and we have our delta 1 dot dot dot, our delta n, and we have our, path 1, and this is our path n.
Delta one again.
Sorry, yeah. It's delta 1 n times. Thank you. Right? So we do indeed get an induced morphism on this one, which is in fact a delta n here. The composable sequence of length n into the composite of the graphs, G vec G dot C. I'll write it up like that to be short. Right? There's an induced map here by the universal property of the colimits. Right? But this is not a solution. Right? Again, this should have been delta 1 here. I think that's a problem up here as well. That's not a solution. That's an n-length path, right? But in fact, what we already have seen how we take that n-length path and collapse it into a single path, which is to say we have our gammas. And so this is the induced composite. And that gives us a laxator by contravariance. Yeah, we took a colaxator and we turned it into a laxator, basically, by contravariance. We're mapping out of things, so we flip the variance. Okay. And that's why we get a lax map up here. This is a lax map. And the laxators here precisely compose our solutions to reachability problems. Now, unlike in the Moore machine case, it's pretty obvious that this is not going to get all of the solutions. And I can give an example of that. Consider this graph and this reachability problem. Womp womp. Consider this graph. If I glue that on, it becomes reachable. So there are solutions to reachability problems in the codomain, which are not solvable in the various domains. I could probably come up with a better one that matches all the boundaries, right? Maybe I should take the time to do that. I did not prepare in advance. But this is a case of emergent phenomena. I forget who exactly, but someone has suggested is a good name for what happens when you have a lax but not pseudomorphism. As in, there's something in the image of the composite, which is not in the composite of the images. Something emerged. The whole is greater than the sum of its parts, or the composite of its parts.
So this only gives you like reachability solutions, which, like for a given decomposition, solve a sequence of reachability
in each component.
In each component.
That's right.
And it can only visit each component once, and it must visit every component.
Yes, it can only visit. Yeah, exactly. So it's a very specific kind of thing. It says that if you can solve all the components, you can solve the composite. It does not guarantee that you can take a solution to the composite and break it down into solutions in the components.
It almost feels like you want to allow, like in the map down to the composition C, you have to send each delta one to precisely one of the G's, but if you could like, skip, like visit, if it could be a non-injective or something where you can.
Yeah, if you were doing something more like a FAM multi-category internal to cat instead of a pre-symmetric monodal category internal to cat, you would be allowed to say visit multiple times. Although in that case, I think you would be allowed to visit multiple times, but you have to use the same path each time. That's maybe not so nice. But yeah, I think that it's probably something you can do to make it better, but you are talking about changing the doctrine.
Yeah,
you do that. That's right. But that is part of the reason to do this representability theorem in such extreme abstraction, so that we can try and squeeze more out of it without worrying about reproving it every single time. Yeah, it is a fairly limited thing, but on the other hand, it is true that the whole is generally greater than the sum of its parts. And there's always a sense in which even when you do get these things to be pseudo, it's sort of because you baked in a lot of the information about how they were supposed to couple together into the boundary information. So ODEs are pseudo, but there's a sense in which when people talk about ODEs being non-compositional, it's usually because when you solve an ODE, you may assume the parameters are constant. But when you couple them, you set the parameters to be a variable function of state. If you could solve the ODE completely generically with a generic time variable parameter, then of course you could just restrict to the ones that do evolve according to the function of the variable of other state. And that is exactly what the representability theorem in that case says. That then the solutions do compose. So in a sense, it's a little restrictive. Nevertheless, it does say that these things compose. And I'm interested in, I think we'll stop here for now, but next time we'll do maybe compositional motifs of a more general character. Because in this case, we had a Colac map from a point, but I think we'll be able to come up with Colac maps from more general double operads, algebras. And then we won't get a single representable functor into omega, but we will get a bivariant one. And we can understand that as giving the kind of compositionality of, say, reinforcing loops and causal loop diagrams or something of that sort. Reinforcing loops and causal loop diagrams would totally work with this exact one I'm doing here, but I think no, no, no. It is you do want to be able to break a reinforcing loop into multiple different kinds of subshapes. And at that point you start to want to have more going on in your domain of the map. You want multiple different kinds of shapes. In this case, we looked at a single shape, which was the arrow representing a path.
If we didn't have these free category morphisms,
Yeah.
could you do something similar instead of taking just delta one or the delta n?
Yes, 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 you can. And that yes, absolutely. And then you would get a bivariate one from that double operator of just the delta n's gluing in exactly the way you said they should glue, which would be linearly. As in you have a double operator where like most of the things are empty. Sometimes they work. There's exactly one way to order a sequence, such a sequence of sequences so that it composes into another sequence. Right? Up to symmetry. And so yeah. Yes, maybe we could go over that too, because it's also kind of interesting. In fact, they have something quite different to say about notions of time. Because I think we covered the notions of time here, but I might go back and reinforce the idea that the way we get notions of time is by sort of not landing in omega, which was span set, but by landing in spans and presheaves. And you'll see that if you don't have a colex map from a point, it's harder to do that. But nevertheless, there's probably still a way to do it. Although that's the subject of active research, so I don't know if I can super duper cover it here, but it could be fun to muddle through. All right, thank you.